So every single time you delete a file on your computer, the universe physically heats up. It's an infinitesimally small amount of heat, but it is real, measurable thermal energy radiating out into the room.
Right.
And for decades, physicists looked at that phenomenon and just concluded that information must be a literal physical substance. I mean, if it burns energy to destroy a bit of data, information has to be tangible stuff, right?
Yep. That was the assumption.
But what if that entire assumption is just backward? What if information isn't a physical substance at all? What if at the most fundamental level of reality, information is actually just the ghost of what didn't happen?
Yeah, and that is the core of the conceptual shift we are seeing at the bleeding edge of theoretical physics right now. We're moving away from a rigid view of physics defined solely by the actualized universe, like the things that undeniably exist, and we're stumbling headfirst into a framework defined mathematically by what could be.
Wow. And that is exactly our mission for this deep dive. We are going to fundamentally change how you view reality itself by connecting three absolutely mind-bending concepts: the multiverse, 3D holograms, and a literal physical definition of counterfactuals, which are the alternatives that were never chosen.
That's a lot to cover.
It really is. And to do this, we are pulling from a stack of incredibly dense sources. We've got the foundational Wikipedia articles on eternal inflation and the holographic principle, and we're pairing those with a brand new, highly philosophical 2026 archive paper by Madera Andra Misha titled "Information is Not Physical."
Yes.
Okay, let's unpack this. Because to truly understand the nature of reality, we actually have to start our analysis at the absolute largest scale imaginable, which is cosmic inflation.
Right, so we have to go all the way back to the fractions of a second just after the Big Bang.
Okay.
In 1979, a physicist, Alan Guth, introduced the theory of inflation.
Making videos isn't easy. If you have the means and the interest, please consider supporting us by checking out the products from the Zero Dimension shop at the bottom left of the video.
Incredibly even, or homogeneous, in literally every direction we look.
Right.
So Guth proposed that the universe underwent this period of violently rapid, exponentially accelerating expansion.
And this expansion was driven by a state called false vacuum energy, right? Like a kind of repulsive gravitational force inherent in space itself.
Exactly. But Guth's original mathematical model ran into a massive roadblock known as the graceful exit problem.
Oh, right. Because the idea was that this false vacuum state was unstable, and it was supposed to decay into bubbles of true vacuum, which is the stable, empty space we recognize today.
Yes.
And these true vacuum bubbles were supposed to expand at the speed of light, collide, and merge to reheat the universe into the smooth cosmos we see. But the math showed that the surrounding universe was inflating so incredibly fast that these true vacuum bubbles could never actually catch up to each other to merge.
Yeah, the expansion of the space between the bubbles was vastly outpacing the speed of light expansion of the bubbles themselves.
Right.
So it left physicists with a theoretical model that produced a messy, cold, fractured universe, which obviously doesn't match the universe we actually live in.
Not at all.
No. So to fix this, in 1982, Andre Linde, Andreas Albrecht, and Paul Steinhardt independently developed what's known as the slow roll model, or new inflation.
Okay.
They proposed that instead of bubbling abruptly, the universe undergoes a continuous, gradual mathematical evolution from the false vacuum down to the true vacuum. It provided a mechanism for inflation to end smoothly and gracefully everywhere.
But physics rarely lets a neat solution sit undisturbed for long.
Very true.
Because just a year later, Steinhardt, along with Alexander Vilenkin and Linde, dug deeper into the math of this new model and uncovered something genuinely staggering. They realized that quantum fluctuations mean inflation cannot logically end everywhere all at once.
Right, because quantum mechanics dictates that nothing is perfectly uniform. During inflation, you have quantum fluctuations in the hypothetical field driving the expansion, which is called the inflaton field.
Okay.
These fluctuations cause the energy density to vary wildly from point to point. So in some regions, the fluctuations push the expansion rate even higher, while in other regions, they cause the field to decay, ending inflation and creating a normal universe.
Oh, I see.
And the profound realization was a matter of simple compounding interest. The regions of space that are expanding faster will always outpace and outmultiply the decaying regions.
Wow.
So the inflating space dominates the total volume of reality, constantly birthing endless, self-reproducing mini-universes in a process that literally never stops.
I always pictured this mechanism like a loaf of bread baking in the oven.
That's a good way to look at it.
Yeah, but the dough is rising at an exponential runaway rate, and as it bakes, tiny air bubbles form inside the dough. And those bubbles represent the regions where inflation has finally stopped, the stabilized mini-universes like our own.
Yes.
But because the dough separating the bubbles is expanding at this violently rapid rate, those tiny air pockets can never actually touch each other. They are completely causally disconnected, forever isolated by the expanding dough. And that is the concept of eternal inflation.
It's a highly effective way to visualize the mechanics. And mathematically, it produces a hypothetically infinite multiverse.
Right.
But this is precisely where the massive scientific controversy begins. Because Paul Steinhardt, one of the very architects of this inflationary model, ended up becoming one of its fiercest critics.
It's fascinating when a theorist turns on their own paradigm. But looking at the sources, his reasoning is entirely rooted in the philosophy of science. Because Steinhardt realized that if eternal inflation is true, space is fractured into an infinite number of patches that inevitably explore literally every conceivable physical possibility. But if your theory dictates that any outcome is equally possible somewhere in the infinite multiverse, then your theory makes absolutely zero specific predictions about what we should expect to observe in our local universe.
And testability is the bedrock of the scientific method. I mean, a theory that predicts everything essentially predicts nothing. It cannot be falsified.
Right.
So Steinhardt argued that this transforms inflation from a robust scientific theory into just an untestable infinite mess.
Which brings us to the rescue mission. To save physics from this unpredictable infinity, Stephen Hawking stepped in.
He did.
In his final paper in 2018, which was co-authored with Thomas Hertog, he attempted to conceptually tame the multiverse. They realized that to restore predictability, they had to mathematically define a boundary for our universe, an exit plane that limits the infinite possibilities of eternal inflation.
Right.
And to construct that boundary, they utilized the holographic principle. So we need to unpack how a boundary actually contains reality.
Well, to understand holography, we actually have to scale all the way down from the multiverse to the densest objects in existence, which are black holes.
Okay.
The holographic principle was pioneered by Gerard Hooft and Leonard Susskind. And the core concept asserts that the complete mathematical description of a 3D volume of space is entirely encoded on a lower dimensional boundary surrounding that region.
So rather than thinking of it like wrapping paper around a box, it's more accurate to think of it like a vinyl record.
Oh, yeah.
Because a vinyl record is essentially a 2D surface with flat grooves, but when you run a needle over it, you reconstruct an incredibly complex 3D symphony of sound waves filling a room.
That is an excellent way to conceptualize the mapping mechanism.
Right.
And this entire paradigm was inspired by Jacob Bekenstein's foundational work on black hole thermodynamics back in the 1970s. Bekenstein noticed a paradox. If you throw an object with high entropy, like a cloud of hot gas, into a black hole, that entropy seems to just vanish from the observable universe.
Which violates the second law of thermodynamics.
Violently violates it, yes.
Right.
The law states entropy must always increase. So to save the laws of physics, Bekenstein argued that black holes must possess their own inherent entropy.
Okay.
But when he calculated, he found something that defied all classical logic. A black hole's maximum information capacity scales with its surface area, so the radius squared, not its 3D volume, which would be cubed.
That is incredibly counterintuitive, because if I want to pack more books into a library, the amount of books I can fit depends on the 3D volume of the room, not the 2D surface area of the walls.
Right.
But Bekenstein proved that the universe's ultimate filing cabinet, a black hole, stores its data on the walls, not in the room.
Exactly. And what's fascinating here is how this geometric revelation leads directly to the famous black hole information paradox. Because Stephen Hawking later proved that black holes aren't completely black. They emit thermal radiation and slowly evaporate over eons.
Right, Hawking radiation.
But according to the math, this Hawking radiation is entirely random. It contains absolutely no information about the gas or stars or planets that originally fell into the black hole.
Oh.
So when the black hole finally evaporates into nothing, does the information of everything it consumed just get deleted from reality?
And quantum mechanics fundamentally forbids the destruction of information.
It does. So Leonard Susskind proposed a solution. He said the information isn't lost inside the volume of the black hole. It stays imprinted as quantum fluctuations on the 2D boundary of the event horizon.
Wait, let's take that a step further, because this is where the implications get massive. If the fundamental information of a region of space is fully contained on its 2D boundary, does that mean the 3D space we actually experience, like gravity, depth, movement, is just an emergent byproduct of that 2D data interacting? Am I a literal hologram like in a sci-fi movie?
Well, it suggests
Making videos isn't easy. If you have the means and the interest, please consider supporting us by checking out the products from the Zero Dimension shop at the bottom left of the video.
With physicist Juan Maldacena.
Okay.
He developed the ABS-CFT correspondence. Maldacena proved that a specific kind of 3D space with gravity, called anti-de Sitter space, can be mapped flawlessly, equation for equation, to a 2D quantum field theory operating on its boundary that has no gravity at all.
Wow.
It was a monumental breakthrough because it showed that the 3D physics with gravity and the 2D physics without gravity are describing the exact same physical reality.
They're just two different mathematical languages translating the same fundamental data.
Precisely.
So the entire universe can theoretically be described as pure information sitting on a dimensional boundary. This aligns perfectly with what the legendary physicist John Archibald Wheeler called it from bit. The concept that every physical object, every it in the universe, ultimately derives its existence from fundamental, binary yes or no bits of information. But this brings us to the crux of our entire deep dive today. Because if reality is essentially constructed of information, we have to ask a very literal question. What actually is information?
And that is the exact theoretical puzzle Madera Andra Misha dismantles in his 2026 paper. Because for over half a century, physicists have widely operated under the paradigm that information is physical.
Right.
This belief was heavily anchored by Rolf Landauer's principle, formulated in 1961. Landauer mathematically proved that the simple act of erasing one bit of information, like resetting a binary 1 or 0 to a blank state on a microchip, must irreversibly dissipate a specific minimum amount of heat into the environment.
And the formula for that heat limit is KBT-ln2. Which ties Boltzmann's constant and the temperature of the system directly to the deletion of data. So there is a literal, unavoidable temperature cost to wiping a hard drive.
Exactly.
Because of this measurable thermodynamic cost, the scientific community largely assumed information must be literal physical stuff. I mean, if it burns physical energy to destroy it, it must be a tangible part of the universe.
That was the logic.
Here's where it gets really interesting, though. Misha completely flips this paradigm. He argues that information is not a physical substance. Instead, it is something he defines as counterfactual structure.
Right. Counterfactual meaning the alternatives that were available but ultimately not realized, the ghosts of what could have been.
Exactly. Misha proposes that information isn't the physical reality of the event that happened. Information is the mathematical structure of the physically realizable alternatives that the event was chosen from.
To deeply grasp the mechanics of this, we have to revisit the work of Claude Shannon, who was the architect of information theory.
Okay.
Shannon formulated the mathematics of entropy in communication, and his core insight was that information relies entirely on the number of available alternatives.
Right.
If a telegraph wire only has one possible message it can ever send, receiving that message gives you zero information because your uncertainty was already zero. You knew what was coming. Information only mathematically exists when a system holds multiple possibilities.
You know, a great way to visualize the mechanics of this is a multiple choice test.
Oh, sure.
The actual information you extract from the test isn't just the physical ink marking the correct answer as C. The information is generated by the reality that options A, B, and D were structurally viable possibilities that could have been chosen.
Right.
If a teacher hands you a test where every question only has one option, bubbling it in requires zero cognitive energy and it transmits zero information, you haven't narrowed down any uncertainty.
And that multiple choice analogy maps flawlessly back to thermodynamics.
Yeah.
Because under Mishra's framework, Landauer's heat of erasure is not the burning of physical information fuel.
Okay.
Instead, it is the strict thermodynamic cost of physically collapsing a possibility space. When you erase a bit of data, you take a physical system that possessed a two-valued possibility space, so it had the structural potential to be a 1 or a 0, and you forcefully restrict it into a one-valued space, a definitive 0.
Wow.
You are paying an energy tax to physically shrink the literal geometry of possibilities available to that system.
You're paying a thermodynamic penalty to destroy alternative futures.
Yes.
That completely reshapes how we view cause and effect.
It really does. If we connect this to the bigger picture, this counterfactual framework elegantly resolves some of the most stubborn paradoxes in modern physics.
Like what?
Well, consider the quantum no-cloning theorem. It is a fundamental rule that you cannot create a perfect, independent copy of an unknown quantum state. But why? we can copy classical computer bits endlessly.
Because classical bits are mutually exclusive decided outcomes. A 1 is a 1. It has already collapsed from a state of possibility into a definitive reality.
Precisely. A classical bit is a realized choice. But a quantum superposition is not a decided outcome.
Right.
Mathematically, it is described by the Bloch sphere, which is a continuous, active geometric structure of probabilities.
Right.
Mishra points out that the reason you cannot copy a quantum state is that you cannot physically duplicate an active possibility structure without interacting with it and forcing it to collapse. You can't photocopy a menu of unmade choices.
Oh, that makes so much sense. And this brings us straight back to the black hole information paradox we discussed earlier.
It does.
Because this raises an important question. If information isn't physical stuff, but just a structure of what could be, why do physicists view information loss inside a black hole as an existential catastrophe for science?
This is where Mishra's theory hits its absolute crescendo. Think about the mechanical reason physicists panic over information loss. Suppose you drop two completely different physical systems, say a complex dictionary and a simple lump of coal, into a black hole.
Okay.
Hawking's calculations show that the black hole will eventually evaporate into the exact same random thermal radiation regardless of what went in. The output is entirely divorced from the input.
They both just turn into generic heat.
Right. But under the counterfactual definition of information, this means two totally distinct possibility spaces, the complex historical alternatives that led to the dictionary and the distinct alternatives that led to the coal have been violently compressed and merged into one single possibility space. If multiple distinct pasts can lead to the exact same future state, then the retrodictive power of physics is completely obliterated. You can no longer measure the present universe and run the math backward to calculate what happened in the past, because the fundamental chain of cause and effect has been mathematically severed.
It's essentially the universe suffering from localized amnesia.
Exactly.
But this is the moment where the entire deep dive harmonizes. Because the holographic principle, specifically Maldaceno's ad SCFT correspondence, is what saves the universe from that amnesia.
Yes, it is.
Because if the 3D volume of the black hole perfectly translates to the 2D boundary of the event horizon, then the possibility structure isn't actually being destroyed. The bulk information, the interior possibility structure of the dictionary and the coal is perfectly encoded on the boundary. The distinct possibility spaces aren't deleted, they are just mathematically translated into a different geometric language and preserved on the surface.
The boundary preserves the integrity of the counterfactuals. Distinct historical paths remain mathematically distinct on the 2D surface of the hologram. It provides an incredibly elegant structural resolution to a paradox that has haunted physics for 50 years.
So what does this all mean? For the listener right now, driving to work or making dinner, how does this actually change reality?
Yeah.
It means physics is currently undergoing a
Making
massive
videos isn't easy.
migration.
If you have the means
We are
and the
moving away
interest,
from what philosophers
please
call
consider
ontic
supporting us by
structural
checking out
realism,
the products
which
from
is
the
traditional
zero
view
dimension
that
shot at
reality
the
is
bottom
built
left of the video.
exclusively out of actual physical entities and the forces between them.
Yeah.
And we are shifting toward modal structural realism. This implies that reality isn't just the collection of actual objects you interact with. Reality is fundamentally constructed from the architecture of what could be. Your modal envelope, the mathematical spectrum of possibilities actually available to you in this universe, is a structural, real part of nature. The unchosen alternatives, the paths not taken, are just as vital to the fabric of reality as the single path you are walking on.
It fundamentally forces us to mathematically respect the ghosts of what didn't happen. And I want to leave the listener with one final, deeply provocative extension of this framework that stems directly from our sources.
Okay, lay it on us.
Andrew Strominger, a theoretical physicist at Harvard, has recently pioneered an astonishing subfield called celestial holography.
Oh, wow.
He is attempting to reformulate the laws of quantum gravity, not on the event horizons of black holes, but by projecting the physics onto the celestial sphere. That's a mathematical boundary at the very edge of an infinitely expanding flat universe. And incredibly, they're beginning to test aspects of this theory using LIGO, which are the observatories designed to detect gravitational waves.
Wait, really? They are trying to find physical evidence of a holographic universe by measuring gravitational waves passing through Earth?
Yes. If information is genuinely the mathematical structure of unrealized alternatives, and that structure is encoded on a lower dimensional boundary, then consider the massive gravitational waves generated by black hole collisions washing over our planet right now. Could these physical waves literally be the ripples of distant possibility spaces radically changing shape, with those changes being projected from the boundary onto our local sky?
Oh my gosh.
When the LIGO detector registers a chirp in space-time, are we physically feeling the collapse of cosmic counterfactuals?
Wow.
It suggests that the boundary of the universe is a dynamic membrane, constantly updating its incredibly vast catalog of what could have been. I encourage anyone listening to look up at the night sky tonight and simply ponder the sheer weight of that unseen architecture.
That is absolutely staggering. The next time you look at a solid brick wall, just remember the physics. It is not just a wall, it is the thermodynamic shadow of every single wall that wasn't built, recorded mathematically on the very edge of infinity. Thanks for joining us on this journey. Keep questioning the possibilities.